This is another emerald out. So in this there is a horizontal wooden block, has a fixed rod OA standing on it. So this is the block they are talking about. And there is a rod which is standing on it. From top point A of the rod, two wires have been fixed to point B and C. So this is one wire, this is another wire. The plane of AOB is perpendicular to the plane of triangle AOC. So this plane is perpendicular to this plane. So this angle is 90 degree between them. There are two identical beads on the two wires. And in the figure, the theta, the two have been fixed at the same angle theta. The wires are fixed at the same angle theta is mentioned in the figure itself. You have a theta here and we have a theta there. One of the wire is perfectly smooth, so one wire is smooth and the other one is rough. So we'll have to figure out which is smooth and which is rough. The wooden block is moved with a horizontal acceleration A that is perpendicular to the line OB. That is again given in the diagram. The acceleration is that way. And it is observed that both the beads do not slide on the wire. So one is not sliding because of the frictions and the other without friction is not sliding. So is that possible? Yes, very much possible. We have done a lot of questions where you have an inclined plane and that is going with acceleration so inclined plane is going with acceleration A, and a block on the inclined plane where there is no friction at all, it doesn't slide down. You might have done it with pseudo force of a MA backwards, which is a component of the pseudo forces able to hold the down force of mg sin theta, or you can do it without pseudo, which is my preferred way of doing. Any which way, so one of the bead is not sliding, that is definitely this bead is not sliding due to this acceleration. And the other one, which will have, if I talk in terms of pseudo force, the other one will have a pseudo force backwards, is if this wire was smooth, then there is no force which is going to stop the mg sin theta along the wire and is going to slide down. So there has to be a friction which holds it up. So it is easy to decide which wire is smooth and which is not smooth. So we'll write a set of equation for the smooth wire. So say this is the blue bead and I'll write the blue equation for that. What I'll do is I'll not write pseudo. You can write pseudo and get the same answer. The forces, the real forces are, you have a normal reaction from the wire N, you have mg of the bead, and the body is going forward with the acceleration because the whole block is going forward with the acceleration and the body is not going up or down. There is no friction. So the normal component of the N, which is your N cos theta, because with the vertical the normal will make theta, balances your mg. So your N cos theta is equal to mg is one equation, and the forward component of N is actually providing the forward acceleration. So N sin theta is equal to ma is the other equation. You can divide the two equations, equation 1 and equation 2, and you'll get your relation of A, a standard relation what comes. So in front of A is sin theta, so A will be sin by cos, which is tan theta times g tan theta. So that's your A. Now we are going to use this A because in the other wire your normal reaction would be not only because of the mg cos theta component, which is somewhat like this, mg cos theta will give a normal reaction. See, it's a 3D drawing. I'm just trying to make in this. If you have any issues, you can ask me. You can indulge more into it and understand. So that is one normal reaction. So I'll say N1. And because of the pseudo force Ma backwards, there is a normal reaction forward here. In real terms, you can say that this normal reaction N2 is the reason why the bead is going forward. So if I say I want to always write in real forces, then I will write my N2 is equal to MA, and A is the same as the earlier A, which is G tan theta. So it is mg tan theta is one equation. This N1 and N2 are 90 degree to each other. I hope you get it. So shall I draw in the front the diagram? If I look this from the front side, the diagram is something like this. The bead is over here. The normal reaction is coming out of the page, which is N2 is coming out of the page, N2, and your other normal reaction, which is your N1, is countering your mg cos theta. So those are the forces, mg cos theta. If I draw, then I have to draw the mg sin theta, mg sin theta. So why is the bead not sliding? Because there is a friction force which is acting against mg sin theta. So how much is that friction force? That friction force is mu times n should be equal to mg sin theta, so that the bead doesn't slide down. And how much is n? N is a n1 square plus n2 square under root, because they are 90 degree to each other. Hope this diagram makes it very clear that they are 90 degree to each other. One is in the plane of the paper, which is your N1, and N2 is coming out of the paper. So your normal reaction is that way. Like in the 3D, I can kind of show you, maybe difficult to show, like this way is your actual normal reaction. So anyways, the bead is rubbing against the wire, and the wire is providing a friction of so much what is written over here, which is equal to mg sin theta, N1 and N2. N1, just to make it clear, N1 is equal to mg cos theta, and N2 is equal to your MA. I have written it somewhere here. N2 is equal to MA, which is mg tan theta, mg tan theta. So doing that, I'll get a mu mg common and a cos square theta plus tan square theta under root mg sin theta. Mg gets cancelled, and that will be your mu value. Okay, that's it. Thank you.